is of vital importance to the metalworking industry. It is the process by which we join metals, and almost any known metal can be welded. Metals of similar and dissimilar characteristics, in many shapes and sizes, and in every conceivable position may be welded. While there are many techniques for doing this, we are primarily concerned with the shielded metal arc welding process, commonly known as stick electrode welding. In this type of welding, an arc is drawn between the work and the covered metal electrode. Before beginning to weld, the operator must have proper protective clothing, including gloves and adequate face protection. Flash goggles are needed in addition to the helmet because one must never expose the eyes to the arc. The required tools are relatively easy to use. Holders are available in a great many sizes and with minimum care will last a long, long time. Modern welding transformers can furnish welding power, either alternating current or direct current, with extremely precise control of the current output. The electrodes themselves are metal rods coated with various substances for use with either AC or DC. There are literally hundreds of types covering a wide range of special requirements from 1/16 to 3/8 of an inch. This electrode handbook gives the specifications for all available electrodes. For good welding procedure, we must memorize 4 cardinal points, and they are length of arc, angle of electrode, current setting, and speed of travel. Now we're ready to try a weld bead. The striking of the arc can be accomplished by either of 2 methods. The simplest one is a scratching motion. The electrode is held near the work, swung down, striking the plate to make contact, drawn out to about 1/4 of an inch, held momentarily, and then brought back to the correct arc length. As the operator gains experience, he'll use the straight up and down movement. It all sounds very simple, but some strange things happen, especially to our character, Joe McGee.
What's this?
Joe McGee's a fraidy cat, afraid to strike an arc.
Oh, go on and strike it. It won't hurt you.
Won't it?
No, go ahead and weld.
Well, now that we know it's safe to strike an arc, let's see what happens when we do. As the arc is struck, it almost instantly creates a temperature of about 6,000 degrees centigrade. This melts both the base metal and the metal in the electrode. The metal melts off the electrode, crosses the arc, and mixes with the molten base metal. The force of the arc causes the mixed molten metal to flow to the rear of the crater, where it cools to form a bead. The movement of this fluid metal toward the rear of the crater and the shape of the crater are excellent checks on the quality of the work. The operator should learn to use them as his guide. At the same time the metal is melting, the covering on the electrode is being consumed. The action is such that a cup is formed in the end of the electrode. This shields the arc and helps direct the flow of metal. A gas is formed surrounding the arc with a protective shield that prevents the exposure of the molten metal to the air and therefore prevents the formation of harmful oxides and nitrides in the deposit. The covering also contains fluxing and slagging ingredients which combine with the ingredients in the molten pool, float to the top, and on cooling form a slag over the bead. These blobs are called spatter. While in this highly magnified close-up photography we see them plainly, they do not represent an undesirable spatter condition. Before we actually join some sample plates, there are a few terms which bear explaining. Undercut. Undercut is a condition where the heat of the arc has melted a channel beside the weld bead and it has not been filled in with weld metal. Overlap is a condition where excess weld metal bulges over but does not even touch the part being welded. Porosity is the condition of a spongy weld bead with holes and pitting due to trapped gases and many kinds of foreign particles. One important guide in recognizing the correct arc is the sound it makes, a sharp, steady frying sound. After the bead has been run and the slag removed, its appearance will definitely tell the operator whether or not the weld bead has been correctly made. In a correctly made deposit, the ripples will be uniform. There will be a smooth bead. It will join the plate with no overlap or undercut, and there is complete fusion and good penetration. This is the result of correct welding conditions. If the arc is too long, the metal melts off the electrode in large globules. These globules wobble from side to side and drop on the work in the form of spatter instead of going to the pool as useful weld metal. A wide, spattered, and irregular bead is formed. The weld metal is left on top of the plate with poor fusion between the base and the deposited metal. There might be some slag inclusions. If the arc is too short, a proper molten pool will not be maintained. There will be gas and slag inclusions. The arc itself will have a tendency to short out and allow the electrode to freeze to the work. The bead is uneven with irregular ripples. It is high. There is poor fusion, and note the gas and slag inclusions. In order to maintain proper arc length, the operator must feed the electrode into the work as fast as it melts off. Since the arc has a definite directional force, the angle at which the electrode is held will affect the control of the molten metal. If held at too low an angle with the line of travel, we are likely to get a distorted bead. If tilted too far from side to side, we'll get a lopsided and crooked bead. In some types of welding, however, this directional force can be used to advantage. Welding power sources can furnish either AC or DC up to 600 amperes for a single operator. They usually have two controls for adjusting current output. When the arc is established, the voltage will drop to a point governed by the arc length. The amperage will rise to a point fixed by the controls set on the machine. On most machines, both controls are used to regulate the amperage. One might be called the coarse control and is used to make broad changes. The other is used to make precise adjustments between the points of the coarse setting. This combination makes possible the setting of any desired welding current. The voltage across the arc is controlled by the arc length and the size and type of electrode used, not by the open circuit voltage setting on the machine. Any variation of the length of the arc will vary the volts and amperage of the arc. Lengthening the arc causes the voltage to rise and the amperage to drop. Shortening the arc causes the voltage to drop and the amperage to rise. It's important, therefore, that we maintain correct arc length and make correct current settings on the machine. Let's begin with the simplest weld in the flat position. The limits of the flat position are 15 degrees in this direction, 15 degrees in this direction, and 30 degrees in either of these directions. Both the size of the electrode and the thickness of the plate to be welded must be considered in making the proper current setting. Here we're using a 3/16 inch diameter all-position electrode, AWS class E6010 with direct current reverse polarity. So with a normal arc, we should have a machine setting of 130 amperes. This will provide us with 26 to 28 volts. It is important in starting the weld that its shape and size be established immediately. Making a uniform weld depends on control of the molten pool. The shape of the pool and the action of the molten metal at the rear of the pool are the operator's guide in making a weld of the proper size and shape. The slagging ingredients combine with the impurities in the molten pool and float to the top to form a slag over the weld. On completion of the weld, the slag is removed. In doing this, the operator should protect his eyes from the sharp, hot, flying particles of slag by wearing some form of goggles. The surface appearance of the weld indicates it has been properly made. The ripples are uniform, the face is fairly flat. Fusion is complete with minimum overlap or undercut. In making long welds where more than one electrode must be used, it is necessary to remove the slag from the crater before the weld is continued. To continue the work, the arc is struck ahead of the crater, and holding a medium-long arc, the electrode is swung back to the rear edge of the crater to re-establish the molten pool. The weld is then continued in the normal manner. The weld has a smooth, continuous face. In order to prevent the possible starting of cracks in the arc crater, it is necessary to fill the crater completely at the end of a weld. An effective way of doing this is to pause momentarily while the crater is filled. Then bring the electrode back over the work as it is drawn away to break the arc. With the crater filled, the danger of crater cracks is reduced. When using direct current, the weld is started with the electrode held at about this angle. During the first few inches of travel, it is changed to about this angle, which is maintained until we approach the end of the joint. During the last few inches of travel, the electrode is brought to about this angle. These changes of angle are made to counteract arc blow, and even Joe McGee has trouble with old man arc blow. Arc blow is particularly troublesome in direct current welding. Notice how the angle of electrode is used to overcome the effect of arc blow. As the weld progresses away from the start of the joint, arc blow decreases, and then the electrode may be brought up to a more normal angle. Notice the absence of trouble from arc blow when the weld has progressed this far. However, as we approach the end of the joint, it is again necessary to change the angle of the electrode to counteract arc blow, which now becomes troublesome from the opposite direction. To make a groove weld in the flat position, the same procedure as used for the fillet weld is employed. The width of the root opening may make it necessary to weave the electrode from side to side in order to ensure proper fusion at the edges. The correct weld has a uniform flat face. Fusion is good. The second layer is made with a similar weaving motion. And the face of this layer, if correctly made, is also flat and uniform. The second layer of a flat fillet weld is made in the same manner as the flat groove weld. Fusion is complete in both types of joints. A fillet weld in this position is considered horizontal. The limits of this position are 15 degrees in this direction, 15 in this direction, 10 degrees in this direction, and 15 in this direction. Again, we must take electrode diameter and plate thickness into consideration before setting the current. With DC reverse polarity, using a 3/16" all-position electrode, a machine setting of 130 amperes will produce 24 to 26 volts with a correct arc. With the joint to be welded placed in this position, the operator strikes the arc and must build up the weld to the required size. The maximum size of a good single-pass fillet weld in the horizontal position is approximately 5/16 of an inch. Proper control of the molten pool is almost always due to electrode manipulation. The weld will have good shape and practically no metal will be wasted. It will join the plate with good fusion, with minimum overlap and undercut at the edges. To review that change of angle, we start with the electrode held at about this angle. During the first few inches of travel, it is brought up to a steeper angle. This is maintained until the last few inches of the joint is reached. Then the electrode is tilted back to about this angle. These changes are made to overcome the effect of arc blow. All of which goes to prove you've got to make them right. Of course, when the weld being made is long enough to require more than one electrode, all slag must be cleaned from the crater. Then, to reestablish the molten pool with the new electrode, the arc is struck slightly ahead of the crater. It is then swung back to the rear of the crater, the pool established, and the work continued in the normal manner. When making a multiple layer fillet weld, the first layer must be cleaned before the second pass is started. In starting the second bead, the size and shape are formed in exactly the same manner as the first layer. This is the appearance of a correctly made second pass on a horizontal fillet weld after cleaning. Note the complete fusion of the second pass to both the base metal and the first pass. It is important that overlapping is not excessive at this point. Of course, the slag must be removed before the third pass is started. Like the other two, the third layer is established for size and shape. At the completion of each pass, the crater must be filled. Pause momentarily to fill the crater, then draw the electrode back over the weld as it is drawn away to break the arc. The completed weld has good appearance and good fusion to the base metal and good fusion between the first, second, and third passes. There is minimum undercutting and overlapping. Note that both the groove weld and the fillet weld have similar face appearance. The horizontal groove weld and fillet weld in the horizontal position are made in exactly the same way with 1, 2, and 3 passes. To review the technique of a weld in the horizontal position, the electrode is moved slightly forward to melt the base metal. Gravity causes the molten metal to flow toward the bottom plate, producing an undercut. This is then filled by moving the electrode back again. As this cycle is repeated, the weld progresses. The gas produced as the coating is consumed protects the molten metal from the atmosphere. The coating also provides the fluxing and slagging ingredients which serve to clean and protect the weld. Now, to summarize, in making correct welds in the horizontal position, proper control of the molten pool depends entirely on 4 main factors: current setting, angle of electrode, length of arc, and speed of travel.